Okay, here we'll start Unit 5 notes. So Unit 5 is all about addition reactions. This is in your ebook, Chapter 5. Our learning objectives are all about understanding addition reactions. So let's just go ahead and start learning about them. In an addition reaction, you are adding something to something else. Right, no surprise there. That's why it's called addition reactions. So in class, I typically would ask students to just look at these two examples. These are two different reactions. One is propene forming 2-bromopropane. One is 1-butene forming 2-chlorobutene. These are both examples of addition reactions. So what do you notice is different about the starting material and the product? Well, one major thing is that we start with an alkene. All of our addition reactions will start with a pi bond, either an alkene or an alkyne, so a double or triple bond. And in the end, we now have a single bond. So that's one thing that changes in these reactions from starting material to product. The other thing is what is being added to the double bond. Well, here, this carbon has a methyl and a hydrogen. Over here, it has methyl and hydrogen and a bromine. This carbon had 2 hydrogens. Over here, it has 3. So this HBr is being added, 1 hydrogen to a carbon, and then the bromine to the other carbon. Same thing is true over here. This carbon that's part of the double bond has 2 hydrogens. In the product, it has 3. Here we have an ethyl and a hydrogen, and then we have those plus a chlorine in the product. So those are all things that are happening in this reaction mechanism. Just to do some highlighting, there's the bromine that gets added, here's the chlorine that gets added, and then a hydrogen for each of these as well. Okay, so let's draw the mechanism to understand how these strong acids, HBr, HCl, can be added to an alkene molecule. So we'll use the example with propene and actually just draw these steps out. So I'm just copying down propene right now. Okay. Now remember that HBr is a really strong acid. We can draw the polar bond or the polarity arrow, this dipole arrow, showing partial positive near hydrogen, partial negative near bromine. And remember, so we're going to do some reaction with this double bond. Remember that the double bond, that's all made of electrons. So these electrons, negatively charged, are attracted to that hydrogen. And so the first step is for the double bond, pi electrons, to create a bond to a hydrogen. Then electrons go from that hydrogen to bromine or hydrogen to chlorine bond back to that halogen. Now that hydrogen doesn't just get bonded in between the 2 carbons, it will be bonded to one of the 2 carbons. It is a specific carbon that it will be bonded to, but we'll draw both options to understand why one of those 2 carbons is favored. So this is going to be our hypothetical. And below that we'll draw what actually forms. So hypothetically, let's say it bonded to the carbon on the left. The new bond would be here, right, from hydrogen that was part of HBr. Now it's bonded to that carbon. And we had to break the double bond right here in order to do that, to form this new bond. Well, now this carbon has only 3 bonds. That makes it a carbocation. But this is a primary carbocation. And that's why this is hypothetical. This is actually not what would form in this mechanism, because we could form a more stable carbocation. So let's just write this intermediate does not form And so you don't even have to draw this. This is only for our notes to understand why it doesn't form. If you're asked for a mechanism, don't draw this version. You would draw the more stable intermediate. This intermediate does not form because it is too unstable. So what would form? Well, that would be if this purple hydrogen is bonded on the right side of that molecule. That new bond to that hydrogen, I'll highlight just so we can keep track of it a little better. That makes carbon on the left a carbocation, but this is secondary. So of our two options, this is what's most likely to form. So I'm actually going to cross this one out. Don't need to even draw it. This is just to understand why, actually to understand Markovnikov's rule, which we'll talk about once we finish this reaction. Okay, now we've got our carbocation. We have also generated this Br minus. And so the Br minus and the carbocation attracted to each other, we'll get a new bond there. And then that generates the final product. And here's our 2-bromopropane. Okay, so that's the product of this addition reaction. You could follow the same steps and find and draw the mechanism for 1-butene becoming 2-chlorobutane. This is one example of an addition reaction. Now we talked about where to add that hydrogen first, and this aligns with Markovnikov's rule. If you have an asymmetrical, unsaturated hydrocarbon, unsaturated meaning double or triple bonds, asymmetric meaning the two carbons, so looking back at propene, the two carbons that are part of the double bond are not bonded to the same groups. So this one has a methyl, this one has two hydrogens, so that's asymmetric. So an asymmetrical unsaturated hydrocarbon, when it comes into contact with HX, where X is a halogen, the X, so the halogen, will bond to the carbon with fewer hydrogen atoms. The hydrogen will bond to the carbon with more hydrogen atoms. And we see that here. Hydrogen bonded to carbon that already had two as opposed to the carbon that only had one. Same thing here, hydrogen bonded to the carbon that had two, this one only had one. This all results in a more stable intermediate, so that's more likely to form. We say that these reactions are regioselective, so this is a new term. Meaning, what's getting added is selective about which region of the molecule it's added to. It's essentially this Markovnikov's rule. The hydrogen will bond to a certain region and the X will bond to a certain region. Okay, let's do the reaction coordinate diagram. Same axes, reaction progress. And then energy. Let's say starting material is here, and I'm just going to put products, same energy as starting material, because we're not given any information about whether it's endo or exothermic. And then we form an intermediate, a high energy carbocation intermediate. So the reaction is 2 steps, one transition state to get to the intermediate, another transition state to get to the product. This is the carbocation, transition state, transition state. So 2 steps. And the rate determining step is carbocation formation, just like SN1 and E1. Let's look at an example with an alkene, with an alkyne. Now usually you can assume you have excess reagent, but sometimes it'll say like 1 equivalent or 2 equivalents. If there's only 1 equivalent, that means for every one of these, only 1 HBr can react with it. For 2 equivalents, that means for every one of these, 2 HBRs can react. So let's understand what happens with an alkyne. I'm going to zoom in here. It will still react with HBr just like the alkene. So again, we have polar bond, partial positive hydrogen, partial negative bromine. We have electrons in this pi bond that are attracted to that partial positive hydrogen, so they'll create a bond, and those electrons go to the electronegative bromine. So what happens here now is we now have a double bond between those 2 carbons that used to have a triple bond. The hydrogen still gets added to the carbon with more hydrogens. So here's our new bond. We've generated a carbocation, and we have Br minus. We have positive carbon, negative bromine. This will go ahead and create a bond to that. And this would be our product over here. So with only 1 equivalent of HBr, the reaction would stop here. So if only 1 equivalent of that HX, in this case HBr, is added with the alkyne, the reaction would stop at the alkene. Now here we have 2 equivalents. So first, 1 HBr would react with the alkyne and produce the alkene, and then the alkene will continue reacting. So first, I'm not going to redraw this mechanism, but in 2 steps, I'm going to draw a couple of arrows to show multiple steps. First, this would form that alkene that we drew above. Then this would react again with HBr. Same steps. The double bond will create a bond to hydrogen. Electrons go to electronegative bromine. We form a carbocation. Hydrogen goes to the carbon with more hydrogen, so that's this new bond here. We have Br minus, and that's attracted to carbocation. So it creates a new bond, and then we get our alkane product. And then this is no longer reactive to an addition reaction. But with 2 equivalents or more of HBr would continue to the alkane. Okay, so when HBr, HCl, HI is added, it followed this mechanism, which is the same as the mechanism up here. Both HBr and HCl are really strong acids. This is going to take us into the next reaction. pKa of HBr is about -8. HCl is also about -8. And that's needed. We need really strong acids to complete this first step when the hydrogen is being donated. So going to the next type of addition reaction, it's a hydration addition reaction. In this case, we're adding H2O. But the thing about H2O is that it's not a strong acid. And so it's not good at giving away a hydrogen. So with just water, just H2O here, we're not really getting any product. So I'll write a note here, little to no product forms under these conditions. Okay, so it's not going to donate its H plus as easily as a strong acid would. So instead, what's added, in addition to water, is something that can make water a stronger acid. For example, sulfuric acid. And often this will have, it'll be above or below the arrow, and it'll have cat in parentheses, which is short for catalyst. Sulfuric acid is a good catalyst. This is a strong acid. Its pKa is about -9. And under these conditions, hydration reaction will occur. When we're understanding what happens here, we have to first consider what the catalyst does. It will interact with water in this case. So you'd have a big beaker of water, add a catalytic amount of H2SO4. It's not a whole lot, but it's enough to carry this reaction forward. So we'll say step 1, consider how the catalyst interacts with reagents / the solvent. Well, when we have water, drawing out Lewis structure, and H2SO4, the structure is on your pKa table, but I'll draw it here. Water has a pKa of 15. We said sulfuric acid pKa is -9. So these two reagents, or the catalyst and the solvent, will go through a proton transfer reaction with sulfuric acid as the acid and water as the base. Water takes a hydrogen from the acid, and we form hydronium, H3O+, and then the conjugate base of sulfuric acid. Now, when sulfuric acid is added to water, because its pKa is so low, it's going to donate its proton to hydrogen or to water, and all of it will convert into the conjugate base and hydronium. So now when we're working through the mechanism, this is the acid that we will consider being added in solution or being present in solution. Its pKa is -1.7. This is what we'll use in the mechanism. So we will have both water and hydronium as part of the mechanism for the addition reaction. Okay, so now let's draw the mechanism. Now we'll start with this alkene, this one that we started with up here, and draw the hydration addition reaction mechanism. Now the first step, just like when adding HBr or HCl or HI, is adding that hydrogen. We need hydronium, the stronger acid version of water, to produce or to give that hydrogen. So here's our first step. Electrons in the double bond take a hydrogen. Those electrons go back to oxygen. Just like the previous reactions, that hydrogen gets added to the carbon with more hydrogens so that we form a more stable carbocation. And then we have water there. Now water, even though it's not negatively charged, that oxygen still does have those two pairs of electrons. And so this is what we'll add to that carbocation. That makes this oxygen positive. So we just have one more step to neutralize the oxygen with a proton transfer. And we have to keep in mind that, remember, there's a lot of water and a little bit of the catalyst. So we still have some of this H2O left over as just H2O. It didn't get protonated. So when we need to remove one of these hydrogens, we will use H2O, which is better at removing a hydrogen than hydronium, which is already positive, so that's not going to take another hydrogen. And there's our last step to form the hydration reaction. And we've got that OH added there. This reforms hydronium, which can continue to react with other alkenes in solution. Okay, I will skip the alkyne learning check. We can go over that in class, or you can try it now. And I'll just add a little bit more to our notes. Okay, last thing to add here for the video are these stereochemical considerations. So if a new stereocenter forms, now this is possible for addition reactions because we start with an alkene and then often end with an alkane. And so if in that process a stereocenter forms, a chiral atom, we look to the mechanism to determine if one or both configurations form. So let's do this example. I will save the next practice for class. So here we have HBr. If we were to just predict the product, which maybe we're not ready for that yet, but I'll do it and I'll draw out the mechanism. But we know that these two carbons that are part of the double bond, hydrogen will add to one, bromine will add to another. So we'll have hydrogen on one, bromine on the other. Hydrogen gets added to the carbon with more hydrogens. Well, of these two, this is the only carbon with a hydrogen, so it's going to add there. Bromine will add here. So just drawing the product, we don't have the alkene anymore. We have a new bromine bonded right there. Actually, just for sake of drawing stereocenters, I'll put it up here. It doesn't actually matter though. Okay, so that's a way to predict the product without drawing the mechanism. The mechanism, of course, explains how to get there, so let's still draw it. And this will help us understand how to determine if one or both configurations are going to form. Okay, so starting material, HBr, double bond, creates a bond to hydrogen. These electrons go back to bromine, and that's our first step. So we have the new hydrogen bonded right here, and we form a carbocation. Then bromine will add to the carbocation to form the final product. Okay, now thinking about stereochemistry. Because this carbocation is planar, I'll put these notes in light blue. Carbocation is planar. So bromide, Br minus, can add, we'll just say above or below that plane. The plane that the carbocation is part of. If you think back to when we first learned about SN1, this is what I'm talking about as far as stereochemistry goes. Because we have that planar carbocation, bromine can add above or below that plane, and that means that both configurations are products. So if you're asked to draw products with proper stereochemistry, you need to draw both configurations. One thing I skipped over is that we have a chiral atom right here. I'm going to use a different color. So chiral, both for this addition reaction, both stereochemical configurations form. So to draw that properly, we would have to draw wedges and dashes at that chiral atom. So here's one configuration, and the other we can switch wedge and dash. Okay, I'll end the video here. We'll do more practice in class and continue our notes, of course, this week.